Hey everyone, and welcome to Miss Estruch Biology. And in this video, I have compiled all of my statistics videos for A-level biology. So if you are struggling with chi-squared, Spearman's rank, or the correlation coefficient, student t-test, or standard deviation, which isn't technically a stat, but I plumped it into this video, then watch along. So I've put together all of the videos I've made explaining this, so it's in one easy place for you to sit down, watch, and smash out those stats. You are basically guaranteed at least one question linked to statistics in your A-level. And if you do want even more help with the math skills, don't forget I've got the entire AQA A-level math skills workbook, which goes through every math skill you need to know, explained, modelled, with common questions, with exam style questions, and with the answers to help you conquer that 10% of your A-level that will be maths. But for now, let's get into it. Oh, and when you get to the standard deviation video, there is actually a correction I've put in the description, so look out for that. It's one of the values should be 10.8 instead of 10.2.
In this video, I'm going to be going through with you just how straightforward it is to use standard deviation in biology, because often it's something that people fear, even if they do study maths. So first thing I just want to clarify, in the biology A-level exam, you will not be asked to calculate standard deviation. It takes too long for it to be justified to be assessed in an exam. You might be asked to calculate it in lessons just to practice the skill, but never in the exam. You could only ever be asked, what is the purpose? So we can see here the definition. So standard deviation is a measure of how spread out all your repeats are from your mean. So you could be asked what standard deviation is and have to give that definition. You could be asked, what is the advantage of using standard deviation instead of the range? So to answer that question, you have to know this definition for standard deviation, but also the definition of range, which is the highest and lowest value. So here are your three key reasons why standard deviation is more useful than range. Number one, standard deviation shows the spread of data around the mean, whereas the range only shows the highest and the lowest. Now, because the range only shows the highest and the lowest, it includes anomalies, and those anomalies have a big impact. Whereas standard deviation, because it's considering how spread out all the repeats are compared to the mean, the effects of anomalies are reduced. Lastly, standard deviation can be used to indicate whether a difference between the results is likely to be significant. And that's the key one we're going to focus on, because that is what comes up most of the time in the exams. So that concept there of significance or not is your answer to why knowing the standard deviation is really helpful for coming to a conclusion. And that's because if, when you've either added or minus the standard deviation from your means, there is no overlap between the two groups or more than two groups that you're comparing, what that tells you is it's likely that the difference between them is significant. Now, you can use this phrase significant in AQA for standard deviation, but it's just key to make sure it indicates it's likely to be significant. It's not a full statistic, so it doesn't tell you that you can be 95% confident that it's significant, but it's likely to be significant. So that's the language you'd use. However, if when you add or minus the standard deviation from the mean, there is an overlap, that indicates that there is likely not to be a significant difference. So an overlap means it's not significant. No overlap tells you it is a significant difference. So let's have a look at two of the most common ways this is assessed, and it links to the critical analysis of data as well, which again is one of the key demanding skills, but I want to try and break it down for you so you can see strategies to approach this to make it less daunting. So a typical start point is they always tell you what the scientists are investigating. So scientists were investigating whether there was any difference in species richness, which is the mean number of species, between three habitats. So we have the result in the table. We have habitat A had 11, habitat B had 8, and C had 1. But they've also included the standard deviation. So this is the spread of the data around the mean. So it could be plus 3.2 from the mean or minus 3.2 from the mean. So the question linked to it is, the scientists concluded that there was no difference in species richness, or mean number of species in the habitat, between those three habitats. Do you agree? And use evidence. Now, whenever you're asked, do you agree with the conclusion, that is saying evaluate the conclusion. So you need to pick out evidence which does support the conclusion, but you also need to pick out evidence which does not support the conclusion. So they're not literally asking, give a yes or no answer. It normally means provide supporting evidence and evidence that contradicts as well. And the only evidence we have are the means. Now, yes, there's obviously a difference between those means, but if you're given standard deviation, your answer is definitely dependent on using standard deviation. And the way to use it is you need to plus and minus that standard deviation onto your mean to see, well, what is the highest and the lowest variation there was compared to the mean. So if you visualize this as a bar chart, the bar would be going up to 11, but you'd have a standard deviation error bar style on top, which went up to 14.2 and went down to 7.8. So we then need to do this for habitat B and C. So 8 plus 2.8 goes up to 10.2, minus 2.8 we go down to 5.2. And then the same for 1, if we add on 1.3 we have 2.3, but it goes as low as minus 0.3. And from doing that, we can see there would be an overlap in the standard deviation bars on that bar chart if we take into account the higher end of group B and the lower end of group A, because this one would go all the way up to 10.2 and this one goes all the way down to 7.8, so they would cross over and overlap. So what that tells us then is the standard deviations for A and B overlap. So that's the way you phrase it. There is an overlap. Then you have to say what that indicates. So that indicates there's likely to be no significant difference between species richness in habitat A and B. So that is our supporting evidence. However, the standard deviation for group C does not overlap with either habitat B or A. And that indicates it's likely to be a significant difference. And in this case, it's significantly lower. So that is our evidence which goes against the conclusion. And that's what they'd be after. They're not interested in whether you actually say yes or no. They want you to use the data to say the two sides of the argument. So this is actually the easier way to visualize it, where you are given the mean and the standard deviation shown on a graph, rather than being shown as a table and you having to calculate the top end and lower end and visualizing, is there an overlap? So this one's much clearer. So again, it always starts with what the scientists are investigating. And this time it's whether there was any difference in the mean glucose production between 3 plant species. And that would be within photosynthesis. They've also told you that the graph is showing the mean glucose production, and that's in grams per minute, and the bars indicate the standard deviation. Now this time it's not do you agree, it's what can you conclude from the results. So the first thing to look at then is, do any of the standard deviation bars overlap? And we can see that for plant species B there's no overlap with A and C, but A and C there is an overlap, and I've done this dashed line to show the top of the standard deviation bar for C. We can quite clearly see it overlaps with A, and the same here, the bottom of the standard deviation of A is overlapping with C. So that would be the first thing that you would state in your answer. The standard deviations for plant species A and C do overlap. Then you go on to say what that means. So this indicates that it's likely there is no significant difference between the mean glucose production per minute for species A and C. However, the standard deviation for group B does not overlap with other species, so it doesn't overlap with A or C, and that indicates that it's likely to be significantly different. Now the final thing I've added is just give a bit more detail, and we can see it is significantly lower. So sometimes the AQA mark scheme does require you to point out, is it significantly higher? Is it significantly lower? And that's it. So you could either get, as we said, the type of question where you're comparing on a table, which is more challenging because it's harder to visualize, or you could have it on a graph, but each time state all of the options where there is an overlap, all of the times where there is not, and then you're stating what that shows you. In this video, I'm going to be going through the correlation coefficient, which is one of the 3 statistics that you need to know for A-level biology. So if you do want a copy of this summary sheet, just click the link in the description to missestruch.com and head over to the maths section. This just goes through the 3 stats and how you would approach any question linked to them. But first, let's have a look at how you decide which statistic should be used. And this flow diagram just takes you through how you know which of the 3 statistics you would be using. And in this video, as I said, we're just going through the correlation coefficient. So if you have continuous data, meaning you're taking measurements, and you're looking for an association or a correlation between those 2 measurements, then it would be the correlation coefficient. So for example, if you were looking at, is there an association between temperature and enzyme rate of reaction? And that's one of the examples we're going to use later in this video. Now for AQA, you don't have to know how to do the statistic for the exam, because that would take way too many minutes of a biology exam on maths. So instead, what they state you need to be able to do is justify when you would use each statistic. So justify your choice. You have to be able to write a null hypothesis for the investigation. And then if they give you the statistic result, you need to be able to write a conclusion. So the correlation coefficient is based on data where you'd have either positive correlation, or if this was the other way round, going from high to low, a negative correlation. And the whole point of statistic is, if we have a look at these 3 graphs, quite clearly, the first one is a strong correlation. Number 2 is a weak correlation. Number 3, no correlation. But scenarios like number 2, if we had just a few more data points lower down, it's then difficult to know, do you have a weak correlation or no correlation? And the statistic enables you to have an answer where you can say if it is a significant correlation or not. So to justify your choice of a statistic, as we said, you would be using a correlation coefficient if you have 2 continuous variables that you're looking for an association between them. So that would be your 1 mark of why would you be using the correlation coefficient. We're going to go through a whole worked example to look at how to write a null hypothesis and the conclusion. And this example is linked to required practical 1, an investigation into the effect of, and I've picked temperature, on enzyme rate of reaction. So step 1, you need a null hypothesis. So this would be, you're stating there is no pattern, and in a correlation coefficient, the pattern is correlation. So we'll be stating there is no significant correlation, and you always have to say between the 2 variables. So between the temperature and enzyme rate of reaction. So this is the null hypothesis we're going to do the statistic based on to see, do we accept that this is correct or reject that it's not and there is actually a correlation. So I've used this particular data. We've got 7 different temperatures from 10 to 70, and here are the rates of reaction. Now, as I said, you don't actually need to know this formula. You wouldn't be asked to calculate it at all, but I am going to go through it with you because you could be asked to use this formula to write up one of your required practicals throughout the course. So this should help with that. So a capital N is the number of pairs of data. So we have got 1, 2, 3, 4, 5, 6, 7 pairs of data. D is the difference in the rank. Now that is what we need to go through. So we are going to have a look at a complete work through example, just to let you know, now I'm using Spearman's rank for the correlation coefficient, and RS is short for Spearman's rank. The RS value will always be between -1 and +1. +1 means it's a perfect positive correlation. -1 is a perfect negative correlation. And if you get 0, it's no correlation at all.
And then you can get values between the 0s and 1, which indicate how strong or weak it is. And then we'll compare it to a critical value table to say whether it's significant or not. Next then, as I said, we'll go through a whole worked example of how you calculate it, in case you need this for a practical write-up. So the first thing you need to do is rank your two sets of data. So you rank it from lowest to highest. So we've got the temperature, 10 to 70 is already in order, so that's already ranked, so 1 to 7. The rate of reaction though is as you took it, as you measured it, so it's not in order necessarily. Now the first one does happen to be our lowest, so 5 is rank number 1, 13 is rank number 2. However, we have at temperature 30 and 70, the rate of reaction for both of those is 28. So if they're the same, they need to have the same rank. And the way that you do this is you look at which ranks they would fill up. So it would be rank 3 and rank 4. And then it is the average of those two ranks. So if we do the average of 3 plus 4, which is 7, it would be 3.5. So that now means position 3 and 4 are taken. So our next highest is 30, and that would take rank 5. 35 is rank 6, and then we've got rank 7. D is working out what is the difference between the ranked values. So 1 and 1, there's no difference. 2 and 2, there's no difference. But then we've got 0.5, 2, 2, 1, and 3.5. Then we square those differences, and then we add all of that column together, so the sum of d squared, and in this case that is 21.5, just adding up that column. And now we can input that into the formula. So 6 times 21.5, and n was our number of pairs, and we had 7. So then if we actually do that stage, this is what we'll be dividing by. And our final RS value is 0.616. Now at this stage, we can't tell if that means we have a significant correlation or not. We know that because it's a positive value, it is a positive correlation if we have one. And it's almost halfway between 0 and positive 1. So if it is a significant correlation, it's a very weak one. To work out then if it is a significant correlation or not, you have to compare your calculated RS value to a critical value in a critical value table. So what we have here is lots of different examples of how many numbers of pairs you might have. For us it's 7, and then you have a selection of values for that number of pairs, and those correspond to p-values. So each of these columns is a different p-value. And what a p-value is the probability, so p is for probability, that the correlation that you have is due to chance or not. And we always have to compare at A level to a p-value of 0.05. And what that p-value means is you have less than 5% probability, so 0.05 is 5%, 5% probability that the correlation you have is due to chance. Or in other words, that means you can be 95% confident it's not due to chance, and therefore it's significant. I'm going to go through that with the results that we have, and hopefully it'll be a bit clearer. So our S value, that was our calculated value. In this example, our RS value is 0.617. We have 7 pairs of data that we were comparing. So we need to read off the 7 pairs of data row. And as I said, you are always comparing to the p-value of 0.05. That is what we call the threshold point to be able to decide if it's a significant correlation or not. And our critical value at that p-value is 0.6786. So a critical value is your threshold point. And what we mean by that is you have to have an RS value either equal to the threshold or exceeding the threshold to confirm it is a significant correlation. So in our example, our calculated value of 0.616 is lower than the critical value of 0.6786, which was for the p-value of 0.5. So that doesn't exceed the critical value. That means we haven't reached or exceeded that threshold. So write in your conclusion then, you would include this statement here where you're showing that you have compared your calculated value to your critical. Then you need to say what that means. So in this case, that means we have more than 5% probability that the correlation we saw is due to chance. And because we have more than 5% probability, that means it's not significant. So we have to accept the null hypothesis. So increasing the temperature did not always result in an increase in the rate of enzyme-controlled reaction, and we do not have a significant correlation. So this is more likely what you'd be asked to do in the A-level exam. Use the critical values table, or they might just tell you your result does exceed a p-value of, and they'll tell you the p-value and you have to state what that means. So p equals 0.05, that is the value you have to compare to determine whether you can accept or reject the null hypothesis. However, if your calculated value was greater than the critical at 0.05 and even lower percentages, then you would put that in your conclusion. So for example, this column, the p-value of 0.01 is 1%. So if your calculated value did exceed the critical value in that probability, that p-value, you'd then be saying there is less than 1% probability it's due to chance, so you're 99% confident. So one more example just to show you how this often comes up, in particular on paper 3. So we've got an example exam question. A student is investigating whether the concentration of glucose bacteria are grown in had an effect on the bacteria population size. And the data we've got then, we can see we've got a scatter graph here where we've got concentration of glucose against the number of bacteria. And the student did a statistic on their data and their calculated value equaled the critical value at p equals 0.05. So that's all the information. The question is, the student, they concluded that the more glucose you add, the more bacteria there'll be. Do you agree with this conclusion? Use all the information provided. So that's really common to be asked, do you agree with a conclusion they give you? And what they're actually asking you is evaluate. So you need to pick out from the graph and from the statistic evidence which supports the conclusion and evidence which would make you doubt that conclusion. So in this example, the first thing is what supports that conclusion. So the graph does show a positive correlation between concentration of glucose and the number of bacteria. So that is one piece of supporting evidence. However, you can see on this graph that the results overlap. And what we mean by that is, for the same concentration of glucose, there are multiple different results for the number of bacteria. And what that means is there was a big range in effect. So that would be evidence that would make you doubt that that conclusion was valid. Next then, we need to use the information about the statistic. So in this case, they said a p-value of 0.5, so not 0.05. So what that means is the correlation coefficient showed there was 50% probability that the correlation was due to chance. Now, if that's 50% probability it's due to chance, that means you can only be 50% confident, and that is no way near enough confidence. You have to be 95% confident to say it's significant. So therefore, this is not a significant correlation, and I've just added in there as well, because you have to have less than 5% probability it's due to chance. So these are really common questions, these evaluate or do you agree style questions.
This video is going through the statistic, the student t-test. So if we have a look at the flow diagram first of all, showing the three statistics that you need to know for A-level biology, there's correlation coefficient, the student t-test and chi-squared. And in this one, we're just going through the student t-test. So you would use this one if you are collecting continuous data, and then you're investigating the difference between the two means of that continuous data. So for example, if you're looking to see, is there a difference between the mean species richness in two different habitats? So with the student t-test, like all statistics in A-level biology, you would not be asked to calculate the statistic in the exam. Your teachers might ask you to do it as part of your required practical, but you don't have to know how to do that in the exam. These are the only three things that they could ask you. So to justify the choice of statistic is what we were just saying, is if you're investigating a difference between two means. So that's what you'd be looking for. This is how you would calculate it. So if you did need it for a required practical, then you'd use this formula, where x is mean 1 and x2 is mean 2. Here is your standard deviation of the first set of data, but you'll have to square it, and n is the number of samples. I'm not going to go through that in this video though. I'm going to be focusing on what AQA and the other exam boards could ask you in the exam. So you would be given the chi-squared value that someone else had already calculated, or you could be given the p-value straight away. If you're given the chi-squared value, you would then need to compare it to a critical value. And you can either have an unpaired student t-test or a paired student t-test, and that determines how you work out your degrees of freedom. So if it's a paired student t-test, that means the two means are from sets of data that were collected from the same individual. That's why we're saying the results are paired. All the data came from one individual, and therefore you automatically have to have the same sample size. However, sometimes you would have an unpaired t-test where you won't necessarily have the same numbers of samples. So with the species richness example that I said, you wouldn't necessarily have the same number of results, and that's why we then calculate our degrees of freedom in this way. So however many repeats you took in sample 1 plus the number of repeats in sample 2 minus 2. So for an example of a paired t-test, a student investigating the effect of exercise on heart rate, and if they were taking all of those results just from one individual, it'd be a paired t-test. So once you then know your degrees of freedom, you would read across. So let's imagine we had 5 degrees of freedom. You would then read across, and we compare to the p-value of 0.05, or in this table they've called it probability value. So 0.05, and you'd have to see, does your calculated value exceed or meet that threshold critical value? So we'll have a go at how you'd write the conclusions. And within your conclusion, you always have to say, do you accept or reject your null hypothesis? Is there more or less than 5% probability that the difference you see in the means is due to chance? And the null hypothesis will be stating that there is no difference between the two means, whatever those variables are. So I've got an example here. We've got a student calculated a student t-test value of 4.82, and we're told that they have 2 degrees of freedom. So we then go to our 2 degrees of freedom row and read across. Now we can't compare to a p-value of 0.10, because that would mean we have 10% probability the difference is due to chance. That is too high a probability that it's just coincidence, that it's just chance. So we always use the p equals 0.05 as our cutoff to decide if a difference is significant or not. And our calculated value of 4.82 does exceed the critical value of 4.31. So we've exceeded that threshold,
that means we can reject the null hypothesis, and therefore that means there is a significant difference between the two means. We know that because if it's exceeded the critical value at p equals 0.05, what a p-value tells you is that is the probability that the result is due to chance. So that means we have less than 5% probability that the difference is due to chance, meaning we're 95% confident that it is a significant difference between those two means. Another example here, a student calculated a student's t-test value of 2.01 with 5 degrees of freedom. So 5 degrees, again we need to compare it 0.05, but this time our calculated value of 2.01 does not meet or exceed that critical value. So that means that it is not a significant difference, and therefore we have to accept the null hypothesis that there is no significant difference between the two means. And that's because if it doesn't reach that threshold, it means we must have more than 5% probability that the difference between the two means is due to chance. So we can't be 95% confident. Now this here is a typical critical analysis style question, and in this example we've got scientists investigated whether there was a change in the communities of 3 different habitats between 2019 and 2020. They measured the changes in mean species richness at those 3 habitats. So mean species richness was their measurement to see if there's a change in the communities. And because it's a difference between 2 means, that is why it'd be student t-test. We've got our 3 habitats, and the first one we can see we've got a decrease for the change in mean species richness. The other 2, it's an increase. The final thing we've been given is a p-value for each of those. And a p-value tells you the probability that that result is due to chance. So we're going to be using those to work out the answer to this question. The scientists concluded that the communities did change. So that's the conclusion they're giving us. Using only the data in the table, evaluate this conclusion. So we have to use these 3 rows of data to see which support the conclusion that there was a change and which, if any, don't support the conclusion that there was a change. So in red is the data that does not support the conclusion. So habitat C, our p-value is greater than 0.05, which means there is more than 5% probability that the increase in mean species richness that we see here was due to chance. And because we've got more than 5% probability, that means it does not show a significant change. The other 2 are both less than 5%. And for habitat B, it's actually less than 1% probability that the increase we see is due to chance. And for habitat A, it's less than 5% probability that the decrease we saw was due to chance. So therefore, there was a significant increase in mean species richness for habitat B, and it was a mean species, there was a significant decrease for habitat A. So for those 3 marks, they'd be wanting you to point out the fact that the top 2 were significant changes. One's an increase, one's a decrease. The bottom one was not significant. And then there would always be a mark for talking about the p-value. So you're showing that you know what a p-value is. So a p-value is the probability that the result is due to chance, and less than or equal to 0.05 is our cutoff to say that it is significant or not. In this video, I'm going to be taking you through examples of chi-squared for A-level biology. So just looking at the flow diagram, we can see how you would choose this statistic. So this is the only statistic in A-level biology that you would use if your data that you've collected is frequencies. And what we mean by that is the data is counting individuals within particular categories. and it's to investigate a difference. So that's when we'll be using chi-squared. Now, as with all the statistics, you don't have to be able to calculate it in the exam. You only have to be able to justify your choice, write a null hypothesis, and write the conclusion. So justifying your choice would be you're investigating, or the experiment is an investigation, looking at a difference between frequency data. So this is the calculation. I'm going to go through it with you because you may have to do it for part of a required practical, but as I said, you don't have to remember how to actually do this in the exam. So this example, we've got scientists are investigating whether there are any differences in the number of ivy plants in a shaded area and a light area. So first of all, the null hypothesis. So this experiment is looking at a difference and chi-squared is looking at a difference. So in the null hypothesis, you'd be stating there is no significant difference, and we say between the observed number of ivy plants and the expected number of ivy plants in the shaded and light area. So you have to include this concept of what you observed compared to what you expect, because in the chi-squared statistic, that is what is being compared. The data you collected is what you observed. What you expect, we typically say would be 50-50 split, so an equal split between the categories. There are exceptions to that. It could be if you've got multiple groups, there are ways that you can calculate the expected. And if it's genetics, you're looking at the number of individuals with brown hair versus blonde hair. You might have expected ratios which link to Punnett square data, but I'll do a whole other video on that because the genetics examples is quite a lot of detail. So we've got our shaded and light area, the number of ivy we observed, the number we expected, and then the formula we said is the sum of the observed minus expected squared divided by expected. So what I've done first of all is the observed minus the expected, then squared, and then the sum of that column. Now we have the sum of the observed minus the expected squared. We can put that data into the rest of the formula. And the last stage is dividing that by the expected number, which in our case was 500. So we end up with a chi-squared value, which is really big here, 71.825. However, that does look correct because we can see we do have a big difference between those two values, so we would expect to get a big chi-squared. The final step is to work out what that chi-squared value actually tells us. And this is where you have to compare your calculated value to a critical value. Now I've just got the column here for p equals 0.05. And what that means is all of these critical values are for a p-value, which is the probability that there will be 5%, or there's 5% probability that the result, in this case the difference, is due to chance. Now to work out the degrees of freedom, it would be our n minus 1, and this time n is the number of categories. Now we just had light or dark area, so that's 2 categories minus 1. So we've only got 1 degree of freedom. So the critical value that we are comparing to is 3.84. We have to see, does our calculated value exceed or meet that threshold critical value? And it does by a long, long way. So what that tells us is, because it's exceeded the critical value at p equals 0.05, it means there is less than 5% probability that the difference between the observed and the expected values is due to chance. Now, if we think back to our null hypothesis, we were saying that the null hypothesis was there will be no difference between the observed number of plants in the two areas and the expected number in the two areas. But we can now reject that null hypothesis because we've proven there was a significant difference between what we observed and what we expected. And we expected there'd be no difference in the two areas. So therefore, this shows us there is a significant difference between the number of ivy leaves in the shade and light areas.